All right, our next speaker is Mutian Wang, and he will be talking to us about a near-resonant adolescent planetary system near the end of photoevaporation. Thank you, Mutian.
Thank you. Hello, everyone. I am Mutian Wang. I'm a fifth-year graduate student from Nanjing University, and I'm also a visiting student at University of Hawaii right now. And today I'm going to talk about our characterization of a near-resonant planet that appears to be at the end of a photoevaporation. So statistics from the multiplanetary systems has given a fruitful information about the evolution histories of these planet systems. For example, one important message from the Kepler multiplanet system is that planets are rarely in resonance. And you can just see some very smooth distribution of the period ratios in these planets, and with some low amplitude peaks around the integer ratios where the mean motion resonance is. And you might have heard from Fay and Finnegan's talk that this migration can give you resonant chains, and this is indeed true. The planets at young ages are usually resonant. So this appears to be in contrast with the mature exoplanet populations. To resolve these tensions, it has been invoked. There has been widespread instability that routinely will disrupt the whole resonance. And some of them may happen when the disk is still around. Some of them may happen when the star is in the main sequence lifetime. But I will not go into every detail of this individual mechanism. Just want you to know that these mechanisms operate on different timescales. And having a young planet younger than 1 gigayears is a very key probe to gain insight to the dynamical evolution of these planets. And I will spend the rest of the talk talking about such case that may shed light on this issue. The system is called TOI 2076. It's a relatively young planetary system with 200 million years old, and it hosts 4 planetary planets with 1 innermost super-Earth and 3 outer sub-Neptunes. And interestingly, all these 3 Neptunes have shown helium outflows, so maybe they are caught in the middle of losing their atmospheres. And thirdly, finally, is a near-resonant chain with their pure ratios very close to 2:1 and 5:3 mean motion resonance. And this feature has given us the opportunity to study their dynamical state, because for the planets near the mean motion resonance usually display transit timing variations. This means that in contrary to a strictly periodic orbit, the planet transit will sometimes come early, but sometimes come late. And this wobbling around the periodic orbits has encoded rich information about the dynamical state of the planets. So this is indeed true for the TTV observation for TOI 2076. For the planet engaged in the resonant chain, B, C, and D, they show a wobbling around the constant period. And for this periodicity has shed light on the dynamical state of these planets. So, for the planet orbits around the mean motion resonance, there can be 2 types of motions. One is the circulation and libration. And they are further characterized by their temporal evolution of the close approach of the planets. So these 2 types of motion also sets the characteristic timescale of their dynamics and will ultimately manifest in the TTV period. So for the system at our hand, it appears that the super period, or caused by the circulation dynamics, is mostly consistent with the observations. And this is indeed true if we map all the system parameters that can reproduce the observation onto the Hamiltonian map. So this is the Hamiltonian map near the mean motion resonance. And here, the resonance librating orbits only exist in this region with enclosed by the red lines here. And any other regions here is the near-resonant circulating orbits. So where is TOI 2076? It's marked in these blue lines here. So the TOI 2076 planets are indeed near resonance, at very far away from the light-braiding resonant orbits. The circulating near-resonant orbits has a profound implications toward their dynamical implications. So for this, I'm showing the dynamical timescale for the orbits in circulation and in libration. So you can see for the orbits in circulation, the dynamical instability timescale will decrease as your eccentricity increases, while the libration orbit stays relatively insensitive to this. So this means that the circulation orbit is dynamically more fragile overall, and the TOI 2076 planets, which is already in the circulating state, might become unstable in the near future as long as its eccentricity can be excited to be a few percent up, which is a characteristic value of the Kepler planets here. Now, okay, so for our dynamical state, we also constrain the masses of all four planets. And it's kind of interesting that despite all four planets have different radius, they share the same masses here. And we can see their equivalently, their atmosphere content increases with their radial distance. So this is kind of in the expectation of the photoevaporation theory, which is thought to conclude at a system age of a few 100 million years old. So this actually has been a really good system to test the photoevaporation here for three reasons. First of all, it is a near-resonant chain, so giant impacts might have not happened to erode the atmosphere. And secondly, the helium outflow is detected, so it is not a pure water world, and at least some volatiles are there. And thirdly, the planets are of similar core masses here. So the planets, this is a really important factor when you're considering the gas accretion and the gas retention during the high energy flux epoch. So the core mass actually measures the gravitational well that you can acquire its surrounding gases when you create the gas. And it also measure the ability to hold on to your overall atmosphere in the main sequence lifetime. So we conduct an atmosphere mass loss experiment coupled with thermal evolution. And in this case, we are simulating all the planets with the same initial envelope mass fractions. And you can see the photoevaporation effect is alone can separate the evolving radius and reproduce the size ordering we observed today. And this can be understood as the differing atmosphere lifetime. Thank you. Lifetime in general. So this means that how long can you hold on to your atmosphere? So interestingly, the atmosphere lifetime has a tipping point around 1%. So if you have a smaller envelope, you will quickly lose all your envelope. If you start with a larger envelope, your radius is so large that you can just receive a higher amount of high energy fluxes and increase your mass loss rate. So you will quickly lose your envelope as well. So this tipping point here serves as a tractor of the evolutionary stage of the radius. So either planets will stop at 1% of hydrogen helium here, or they will just completely lose all the envelope away. This is what happens for the planet B and E here. And for planet C and D, they are more distant, so they are not severely sculpted by the photoevaporation. So that brings the summary of my talk. In this talk, we bring the precise dynamical characterization for a very young exoplanet system. We show it is in a fragile neo-resonant circulating dynamical state. And we also show it shows a sign of differential photoevaporation atmosphere mass loss process. Thank you.
We have time for one quick question as the next speaker comes up. Laria.
Yeah, thank you. This was a very nice, these are very nice results. I was wondering, sorry if I missed it, but can you constrain the efficiency of photo evaporation?
Actually, the efficiency is a variable for this because if you have to constrain the efficiency, you have to assume an initial value here. And higher initial envelope mass fraction can give to produce the current the radius here, you need a higher efficiency. So it's highly variable for now. But actually, it's in the range of 5%, something I would say.
All right, let's thank Mutian again.